Thanks everyone for coming here. We're super happy to see you. Thank you for making the time to be here. I know that especially in industry, there are always crazy deadlines, customers sending emails. So we really appreciate you making the time. So as you can see, we are in this beautiful space. So I'll give you maybe a little bit of history about our department. So we used to be the Department of Computer Science and Engineering for the longest time, and we were located across the street in the Paul G. Allen Center for Computer Science and Engineering. And recently, we had the great opportunity to become a school. So we are now the Paul G. Allen School of Computer Science and Engineering. And in January, we moved into this beautiful space, which is this building called the Bill and Melinda Gates Center. So now we are across the two buildings, and you can kind of hear the theme right here. So thank you, Microsoft, for all your help and everything. Thank you also to all the other donors. So this is not, we're not, but Microsoft definitely has a bit of a special place. So in terms of the database group, we are super happy to have you here. A couple of years ago, we started an industrial affiliates program for the database group. And the goal is really for us to grow, strengthen our connections with industry, especially the local industry. Seattle is a great hub of technology. It has been growing. It's a very exciting place. And we really want to make sure we have close connections between the academic side and our group and also the industrial side. And the workshop today is really only for companies that are affiliated with our group. In January, February, we have a second event, which is the Northwest Database Society annual event. This one is open to everyone. We will re-invite you for that one. But today is really a little bit more special. And it's a day where we like to share some of the recent, exciting, still half-baked research so that you have an early preview into what we are doing. So again, thanks everyone for being here. Now more specifically in terms of logistics, the restrooms are just outside. So if you go outside, there's a big purple sign that says restroom. The sign for the restroom is like a modern sign, so you have to expect to see a different kind of sign. If you call the elevator, be careful because the emergency button is where the elevator button should be. So when I brought my kids here on a weekend just to show them, of course my daughter pressed the emergency button. So yeah, don't do that. The other thing, I think those are the main things. And finally, in terms of the database group, we have several students with us today, so maybe you guys can just raise your hands, the database students. We have several postdocs, so yeah, database student postdocs, which is really great. And we have 3 faculty. So again, my name is Magda. I'm a faculty here focusing on database systems. Dan is my colleague. He's focusing on database theory. And we are super excited to announce that we have hired a brand new faculty, Alex Ratner. He's actually so recent that he's still wearing all the UW gear, although. So we appreciate that. But Alex is coming to us from Stanford, and he works on systems for machine learning. So a very exciting area, and we're very happy to have you here. So again, thanks everyone for being here. I'm going to pass it over to Dan to introduce our keynote speaker. Thank you.
Thanks, Magda. So it is my great pleasure to introduce today Molham Aref. Molham is a successful entrepreneur. He brought several companies to success. He is extremely well known, of all places, in the database theory community. Not just because he was always friendly to the theory that came out of the theoretical community and transferred it to real products, but it's actually Logic Blocks, his latest company, is famous for having implemented the first theoretically worst-case optimal join algorithm that is only now slowly making its way into industry, as far as I know. So today, Molham is going to talk about his next great startup, RelationalAI.
All right, thanks. And I appreciate being invited, and I appreciate your committing your time here to my talk. I am representing the work of a lot of people, okay? So I don't want to take any credit for this work. In fact, one of the people who's done a lot of the work here is Max, who's sitting in the back. So I realized just now that perhaps Max and I should have coordinated because I might have some of his slides in my talk, but well, hopefully we're going to be okay. And so we're organized in terms of having a product organization, a data science organization, and a faculty network. And we've worked with faculty from many different universities in sort of different capacities. Okay, and as Dan said, I've personally been working in machine learning for 28 years, going back to a company called HNC Software out of San Diego in the early 90s. This was sort of the second resurgence of neural networks. We were building credit card fraud systems and credit card fraud detection systems. HNC went on to go public and become part of FICO. I was at a company called Retech that went on to go public and be acquired by Oracle, and a bunch of other companies that, 5 of these I've personally been involved in, and Demantech, which was acquired by IBM. Several of my colleagues were there. Okay, so we've seen both the technical side of machine learning, the scientific side of machine learning, as well as the applied side and industrial side. How do you actually build machine learning-based applications to solve real problems in industry? And it spanned the financial services industry with fraud, retail industry with supply chain revenue management, the telecommunications industry with wireless network optimization, and other applications as well, computer vision applications. Okay, so today I'm going to be making the case for a new category of technology that we're calling relational artificial intelligence. Okay, and this is, much of this has existed in the research community. I don't believe any of this has been commercialized, and so what we're doing, what we spent the last 20 months as we built our company, is to try to put the technology and the team together so that we can provide this in an industrial strength way to people in industry. Okay? And I'll start by asking you a question or making a statement about, well, what if I tell you databases should be relational? Is that controversial at all? Obviously not. It is controversial in the sense that not all databases should be relational, maybe, but generally speaking, we've accepted the relational model that Ted Codd brought us, 4 decades ago. Okay, but with the time that he proposed it, this was far from an accepted idea. Okay, the Googles and the Facebooks of that era, IBM, Honeywell, GE. We're making a lot of money off what was called navigational databases or hierarchical databases. And Ted's proposal seemed very academic, non-practical, and so on. In fact, there were debates about it, and there was at SIGFIDET, which is the precursor to SIGMOD, in 1974, Charles Bachman, who was already a Turing Award winner, represented the navigational camp. And at the time, he also represented industry, and he had written this database called IDS, which is basically the Oracle of its day, and was arguing against relational databases and for navigational databases, basically around, hey, performance. This relational stuff is never going to perform. And then 2, programmers understand, navigation and pointers and chasing pointers around. They don't understand relations and sets and stuff like that. And you're dreaming, Ted, that this is going to go anywhere. Ted, on the other hand, hadn't won his Turing Award yet. He was sort of unknown researcher at IBM, and he was arguing from the perspective of separation of concerns, and if you can separate the what from the how, you can ultimately get the performance. And he was also arguing you shouldn't worry about programmers. They're prima donnas, they're expensive, they're hard to find. You should be using relational algebra and SQL to make it possible for normal people and domain experts to do database type stuff. Okay, so who won? Well, we know who won. This is the Oracle, which was started out life as a company called Relational Software, Inc., launched the first relational database in 1979 and IPO'd in 1986, and is now worth around $190 billion and steadily growing. At the same time, a company called Ingress was created, commercializing the work of Michael Stonebreaker and his peers at Berkeley. It was led by my current partner, Gary Morgenthaler, who was 39 at the time, who was CEO, and it launched in 1981 and went public in 1988. And when it was initially formed, it was called Relational Technology, Inc. In fact, you can see the name here on the S1. Okay? So you had relational software and relational technology as two companies. They got created and they got to establish a new category of technology called the relational database. Okay? Before that, that category didn't exist. Databases existed and so on. Okay? And we all know that if you look at any list of popular databases, you see the usual suspects that typically track their roots back to one of those two systems or work done at IBM and Almaden. And if you go and ask an analyst about navigational databases, this is sort of the magic quadrant for databases, and generally you don't see that. Okay, you're seeing a little bit of a comeback of that navigational idea in some graph databases, but generally the bulk of the world's information is stored in relational databases. Okay, so I leave it to you to think about why that happened. Why did the relational model, this sort of mathematical, weird thing that you can imagine not being very accessible, okay? Why did it win? So let me ask you a different question. What if I ask you or tell you, business intelligence should be relational? Okay, well, duh. That's not controversial. But in the 90s, it used to be extremely controversial. It used to be, there were the MOLAP versus ROLAP wars, right? MOLAP stands for multidimensional online analytical processing. The multidimensional is referring to multidimensional arrays, or what today we would call tensors. Okay, and all the incumbents in the BI world were doing MOLAP. Why? Because arrays, we can do fast things with arrays. Arrays are fast. We know how to do get performance with arrays and tensors. And relational is never going to be fast enough. You're smoking something to. Okay, well, who won? This is the Tableau chart until they were acquired by Salesforce a month ago. And Tableau doesn't have relational in its name, but it has Tableau in its name, table, right? So paying homage to its relational roots, okay? And again, if you go to Gartner and say, tell me, I want a MOLAP business intelligence system, they just don't exist, okay? So why? Why did the giants of that era just disappear, and why did the relational model win? All right? Now, what if I tell you artificial intelligence should be relational? Okay? Now, I'm high. I'm smoking something. There's no way this is the case. Relational systems are too slow. Tensors and linear algebra are the way we've always done it. For crying out loud, the most popular machine learning system out there has tensor in the name. You are smoking something. Okay? And I'm here to tell you that relational artificial intelligence is inevitable. It is as inevitable as relational databases and relational business intelligence. Okay, so that's the claim. So why? Well, artificial intelligence in general has been made possible by advances in performance, and there's a sort of strong need for speed that drives machine learning and AI. Okay, and some evidence that I have to share with you here around that is that I saw an interview recently by Reid Hoffman interviewing Greg Brockman, who's the CTO of OpenAI, and Greg said he's following 47 different hardware startups that are building hardware for accelerating AI. Okay, in Barron's, I saw an article that said there are 13 private chip companies focused on AI markets that have raised over $1.2 billion to build chips that eke out a little bit more performance to support AI. Okay, Greg Dimas, who used to be an intern and was at Baidu until recently, is quoted in EE Times as saying that if we had 100x more performance, we could do really amazing things with AI. Okay, and I would argue that many of AI's biggest challenges are computational. Right? If you want more accurate models, then you want to do things like look at more data, or you want to use more sophisticated algorithms, or you don't want to make IID assumptions, et cetera, et cetera. So you need more compute. You want more interpretable models. Now you're not just searching for models that minimize the loss function. You're now searching for models that minimize the loss function and have satisfy some criteria around interpretability, like their decision trees that don't have depth more than 7 or something like that. It's harder to find a model that is accurate and interpretable computationally than just one that is accurate. If you want versatile models, generative models, where you can infer what you want to know from all the things that you know, go in any direction, that's computational. If If you want explainable models, like building a neural network that explains another neural network, well, then you have to build a second neural network. Well, that's computational. And robustness and fairness and Jan LeCun's self-supervision and causality and so on. Many of these things require or have heavy computational requirements at their core. Okay? So how do you get performance? There are two ways to get performance, broadly speaking, in computer science. There's the do the same amount of work, but do each unit of work faster or do them in parallel. Okay, get more workers to do the same amount of work or get better workers to do the same amount of work. So this is all about constant factors. These are techniques like latency hiding and managing your memory hierarchy, parallelism in various forms like SIMdification and multi-core accelerators, and then specialization, right? Remove the interpretation overhead. Take advantage of the fact that you know a particular data set or a particular query and then specialize your evaluation for that. All of these things are great. They're all very important, and that's where a lot of energy goes in machine learning these days, is to try to do more and more of this kind of stuff to get performance. But there's another way to get performance and to get scale. And in my view, that's the better way, the more elegant way, which is just to find ways of doing less work. Look at the asymptotics of the problem, come up with better algorithms. Tony Hoare, won a Turing Award in part for inventing quicksort and making business applications practical, because now you had an n log n sorting algorithm versus an n squared sorting algorithm, right? I can run quicksort or merge sort, in an interpreted slow language and still run circles around bubble sort implemented on top of GPUs, et cetera, if my data set is big enough. Okay, so the asymptotics, come into play when you can now come up with algorithms that exploit problem structure, algebraic structure or combinatorial structure or statistical structure or geometric structure. Okay, that's why we're fans of a lot of work that happens on the theory side, because these kinds of problems are interesting on the theory side, whereas these kinds of techniques are more popular on the systems side. Okay? Other ways to do less work is to take a hard problem, map it to an easier problem, solve the easier problem, and hopefully you have your solution to the easier problem approximates the answer to the hard problem. Okay, and there are other techniques. All right, so brains versus brawn. Both are important, okay? But let's start off by talking about brains a little bit. So here's the ironic thing. So I mentioned, the database wars and relational databases, started to become popular 40 years ago, and humanity has spent, I don't know, hundreds of millions of hours creating relational models and curating them and carefully adding data to them. And in fact, if you didn't have these relational databases that had all this data, you wouldn't be able to do machine learning in the enterprise, because data is the input to machine learning. Okay? So what's the first thing that you do when you do machine learning in the enterprise? The first thing that you do is you work really hard to throw away all that hard work. Okay? The input to every machine learning system out there, every single one, is a flat table that has a billion examples and maybe 1,000 columns or whatever, that you have to create by joining together all your relational source data or your semi-structured JSON data or whatever. Okay, which JSON documents have structure too. You can model them relationally. I mean, when I say relational here, I mean mathematically relational, not SQL. Okay, so you throw it all away. Okay, so you work really hard to create the structure, then you work really hard to throw it all away, and then you ask your machine learning method to work really hard to reconstruct some of the structure that you just worked really hard to throw away. Does that sound like a good thing? Okay, of course it's not. And sorry. Yes, exactly. Chip companies love it. And it's actually worse than that, okay? Because, the relational model, you can do things like assume falses or assume zeros in many cases, and the machine learning needs to see needs the zero filling, right? So you end up actually creating more rows in this design matrix, okay, to kind of put in the zeros, right? In the relational model, if you didn't have a sale of an iPhone in a particular Best Buy store on a particular day, you just have a missing record. But the machine learning needs to see that there were zero sales. So you have to kind of make this data even bigger, more denormalized, okay? And then if your data is categorical, like you have a brand, okay, so your smartphone is an Apple or a Samsung or a Google or whatever, you can't really give that as an input to the machine learning. You have to give it numeric input. So you typically would want hot encoded or something like that. So you would have a column for, is it an Apple or not? Is it a Google or not? Is it a Samsung or not? Okay? So you're adding a whole bunch more columns and a whole bunch more rows in this translation as well. Okay? So let's revisit this from first principles, as I'm sure hopefully this offends you. Okay? And let's see how you might look at this from a relational perspective and a relational database perspective. Okay? Well, if you're a database person, you look at that thing on the right-hand side there, and you say, well, that's just a view on this. Okay? And I don't have to materialize this view. Okay? I can just define the view. I can have a feature extraction query that defines that thing in terms of this. Okay? And we all know from our first database course that I can push certain operators through joins. I can push filters through joins, for example. So instead of joining two big tables and then filtering the result, I can push the filter through, filter each of the two tables and then join the results. I get the same answer, but I do it in much less work. Okay? So can we push gradient descent through this view and have the optimization that defines any machine learning method, okay, that's minimizing the loss function, work here? Okay, and Max and our colleagues Hung and Mahmoud and Dan and other people who are on our team and our faculty network have answered that question in the affirmative. Thank you very much. And for not every machine learning method, but for a large class of machine learning methods, this can be done. And in fact, you typically only need to visit scan the relational data in raw form once, and you compute these aggregates that generate sufficient statistics that you can then do your gradient descent on and learn the parameters of the model. Okay, different models require different types of sufficient statistics. I'm not going to dwell on this, but you have to compute different sets of aggregations. And in fact, the relational structure really helps you in computing the sufficient statistics, because let's say you were trying to compute information that aggregates from sales by item to style, and then sales by item to subclass, and item to class, and item to department, and all of that. You can use the same OLAP tricks that we know how to use, and you can go, okay, aggregate from item to style, but instead of going back to item to get to the subclass, go from style to subclass. And then instead of going all the way back down to the raw data to get from item to class, go from subclass to class. Okay? And so wherever you have a functional dependency, you can exploit that to basically leverage aggregation work that you've already done in aggregation work that you need to do. Now, TensorFlow cannot see that. It has no idea what the structure is. It cannot make any assumption. It's kind of like bringing a gun to a knife fight, right? It has to assume that my iPhone isn't always an Apple. It's an Apple today, but maybe it's an Apple. Maybe it's a Samsung tomorrow. Okay, or depending, it changes brand depending on store or something like that. Like things that we know cannot happen, TensorFlow does not know that they cannot happen, and so it has to kind of go on and consider those possibilities. Okay, so let me show you a very simple example, work done by Max again. So a very simple relational schema around a retail data model. This is extremely unrealistic in that it's much simpler than a real data model. A real data model looks more like that relational schema I showed you earlier, but let's roll with it. This was a toy example anyways, just to make the point. Let's say I have inventory or sales data. In this case, I have 84 million records of inventory. Let's say I have 5,600 items, 1,300 stores. I have demographic information that are keyed by zip code, and I have weather information that's keyed by store or zip code day. Okay? And in order to create the design matrix, I join it all together to create a table that has 44 columns. 3 are the key, the item, the store, the date. And then 1 is the thing that I'm trying to forecast, which is, let's say, sales or inventory. And then the other 40 are features into my model. Now, this is extremely unrealistic because you would never use the raw features, the raw data as features. You would have to do a lot of feature engineering around it. But I'm trying to make a point here. Okay, so And for that point I'm trying to make, you don't need to do a lot of sophisticated feature engineering. Okay, so my 2.1 gigabytes becomes 23 gigabytes after I've joined it all together to create the design matrix. Okay, and it takes 217 seconds in Postgres on one core to join it all together, and 373 seconds to export it, and it takes me 12,000 seconds to do one pass on this data in TensorFlow to build a basic regression model. Okay? So now let's do it the relational way. So in the relational way, where's my cursor? I've lost my cursor. The 2.1 gigabytes stays 2.1 gigabytes. I don't need to join anything together. I don't need to export anything. I do need to compute the sufficient statistics, but because I'm exploiting all that relational structure, it takes me 18 seconds to compute 40 squared sufficient entries into the covariance matrix. Ask Max again. And that generates data that's 37 kilobytes in size. So I've taken 2.1 gigabytes and created 37 kilobytes of sufficient statistics. And then I do my gradient descent on that. And guess what? In half a second, I learn the same model that TensorFlow took 12,000 seconds to learn. Okay? So this is not an approximation. In fact, we're better because TensorFlow is so slow, we did one epoch, one iteration. We did not keep iterating until we converged on the parameters. We just did, I think there were 84 million records, and so we did like 84 1 million record batches, okay? In the relational says, we like splurge, keep going until you converge, until the parameters don't change anymore, okay? So actually, we might have a slightly better model. So that's a lot faster. So 18 and a half seconds to produce your first model versus 12,500 seconds. Okay, that's 676 times faster. In fact, once you've created this, the sufficient statistics in the covariance matrix, you can consider any model with any subset of those 40 features in half a second. Right? So in TensorFlow, if you decide, well, what if I want to try these 38 features? You have to do another 12,000 seconds to see whether you get a better model or not. Here, you got any subset, you've already computed the sufficient statistics, then it's half a second for every model thereafter. So if you're trying to automate aspects of the feature engineering, that can pay off. Okay, like I said, the two big caveats here, this doesn't work for everything. It works for these methods. The loss function has to satisfy certain algebraic properties. The relative speed up starts to come down as you do more and more feature engineering and you get more and more sophisticated features, okay? So don't walk out of here thinking that we do 1,000x faster, 10,000x faster in general. That's just an extreme example to make the point. But you should walk out of here thinking that, I don't need to do the joins, I don't need to do the exports, and if to the extent there's redundancy, to the extent that the design matrix is bigger than the relational model, I should get a speed up that's proportional. Okay? So what? Well, if you go to NVIDIA's website, GPUs give you, according to NVIDIA, okay, which is has to be optimistic about this, a GPU implementation of machine learning gives you 2 to 10x faster performance than a well-engineered CPU solution. Okay? So, in Moore's law terms, that's 3, 4 doublings, right? So 3 doublings, let's say, 2 to the 8 is roughly 10. So 3 doublings. So a GPU it gets you a computer for machine learning that's 5 years from the future. Okay? If you're 1,000x faster, then that's like getting a computer from 15 years in the future. Okay? And as a business, do you want to be running your business on a computer from 15 years in the future or from now? Okay, that's kind of the intuition I'm trying to give there. Okay, and this, let's say it's only 10 times faster. Let's say it's GPU speed, right? There's still billions of dollars that go into making it faster, and again, you bring it back to the kinds of problems that you can now start solving more effectively because you have that speed. Okay, so that's point number one, is the relational structure gives you performance. Okay, for certain methods, under certain situations, and so on. All right, point number two. What else do you throw away when you build that feature matrix? Okay? You throw away a lot of prior knowledge, okay, that you could use in sort of an Bayesian prior sense. You can use to build better models. The semantic information in here about how things are structured that, in principle, you can use as a starting point for your modeling. And you can also start using to understand relationships between things so that you don't have to make the IID assumption, which is the assumption that everyone makes when you're doing machine learning, that every row, every example is independent of every other example. Okay, well, I've had real businesses, like my former customer Sainsbury's in the UK is a grocer. They sat down with me and say, look, we have this thing that when it happens, we hate it. The person who manages organic fruit is different from the person who manages non-organic fruit. And when this person promotes the organic blueberries, the model that drives demand for the non-organic blueberries doesn't know about it because it's just looking at the promotional strategy for the non-organics. And so they don't understand that there's this cannibalization relationship between organics and non-organics. And so we end up throwing away a lot of perfectly good normal blueberries when we promote the non-organic blueberries, unless we manually look out for that. Okay? And this cannibalization effect, yeah, obviously it's clear between organic and non-organic blueberries, but what about organic blueberries and non-organic strawberries, or cherries, or bananas, or mangoes? In fact, Sainsbury's is famous in the UK for heavily discounting wine because in the UK people generally enjoy their wine, and so if you give if you give out a good deal on wine, a bunch of people come to your store and they buy a bunch of other stuff, so you still end up making money. So there's a dependency between the price of wine and sales of popcorn. Okay, so relationships matter. Predicting whether I'm going to have a heart attack or not could be helped by knowing whether my dad had a heart attack, or my brother, or my sister, or my mom, or anyone in my family. Relationships matter, and all those relationships are thrown away when you flatten, and you have to put them back in by hand with feature engineering. Okay, so why do that? Why work really hard to describe the relationships and then work really hard to erase it, so that then you have to work really hard to add features to add them back in? It doesn't make sense, right? Anyway, so if you take this idea to the extreme, you end up thinking you can think of the database as just one example, one instance that you're trying to learn from. This is obviously computationally very challenging. You can also think about the language that you use to talk about your schema as a language for your ontology, for your domain, that lets you now start to express features very easily that allow you to generalize things. So you don't have to say organic blueberries cannibalize blueberries, organic strawberries cannibalize strawberries, organic cherries cannibalize. You can say organic fruit cannibalizes non-organic fruit. That's a feature, okay? Because I can quantify now over things. That's important. Or I can now predict link-based patterns, right? Like inter-item dependencies, okay? Or I can live in a world where for blueberries you have 3 things that cannibalize you, okay? But for, I don't know, for peanuts, I have 20. Okay, there's a sort of varying, or I have 3 people in my family, Dan has 30. Okay, it's very hard to do in a design matrix to kind of add support for a variable number of columns, if you know what I mean, right? And so having a relational language that lets you describe features that are sort of vary is very important. Now, in this world, inference is very hard, and learning is harder, and computational and problem. Okay, people who push for this kind of machine learning, who was from UW, and for a long time, evangelized this whole idea, but never really caught on, in large part because you couldn't really solve real problems with it because it didn't scale. Okay, and one of Pedro's examples is this sort of model around smoking and how you would describe the fact that whether you smoke or not is related to whether you have friends who smoke or not, and things like that, right? So you can take your normal schema, right, written in a data log style here, and say, all right, I have persons, I have smokers that are a subset of persons, I have people who have cancer that are a subset of persons, and then I have a friends relation, which is a relationship between 2 persons, okay? But if I wanted to encode the knowledge that smoking causes cancer and that friends have similar smoking habits, I can just keep using the same language that I used to describe my schema to say, hey, it's not always the case, but so it's soft information, soft logic, right? If you smoke, you get cancer. Or in the retail context, if you raise prices, demand goes down. Or if you promote the organic stuff, the demand for the non-organic stuff goes down. All this is prior knowledge, okay? So Alex is here and will be telling us about Snorkel, which is I love the system because it lets you basically capture prior knowledge that's maybe generally true, but not always true. And then you combine lots and lots of bits of that prior knowledge, you can put it together, and guess what? You kick butt. Okay, I saw something yesterday. Jan LeCun tweeted something about a Facebook model for natural language processing, and you look at the leader chart, and snorkel metal is right at the top of the leader chart. Okay, so anyways, now the trick is how do you make this stuff fast? And there are many different ways, and a lot of ways tried by people who are not at our company. Like Lisa Gatour has tried to sort of approximate this, reformulate the problem into one that is becomes where the search becomes a convex continuous optimization, and approximate the answer that way with probabilistic soft logic. People have tried to do lifted inference and approximate lifted inference by exploiting group symmetry in the problem. Our approach basically is about to try just avoiding the grounding altogether, right? So this design matrix construction is like grounding and optimization, right? So what we're doing is we're doing the optimization on the relational structure as opposed to having to ground, right? Grounding is one of the expensive steps in SRL, and if you can avoid it and actually do the optimization on the raw data or the structured data, you're better. Or there's another thing that Max and Dan Olciano started to think about, which is, if you look at SPNs and other ways of doing this kind of machine learning tractably, one of the inside steps in learning a structure of some product network is to figure out how to group rows of information together, okay? And that's often done by clustering. You run a k-means clustering or a clustering algorithm in the inner loop of this learning algorithm to try to bring rows together so that you can sort of exploit common characteristics. Well, if you don't have the semantics of your database, okay, you can't cluster any other way. But if you have the database that tells you, hey, smartphones fall in a category, or an iPhone and a Pixel and a Galaxy fall in a category called smartphones, now you have a cluster. I'm taking semantic information from the database, and I'm using it to group information based on human knowledge of a domain, okay? And that might not always be ideal or perfect, but that's better than me trying to sort of arbitrarily group things together based on, k-means. At least that's the hypothesis. Okay, so let me pivot. So I showed you, hopefully the second point I made is when you throw away all that relational information, you're throwing away semantics that are important for your problem. Okay, let's talk about Braun, because the knock on databases in the machine learning context, well, relational systems are too slow. Okay, and by slow, what we mean, what typically is meant, they don't do the constant factor type optimizations that matter. Okay, and again, as a quick reminder, it's about memory hierarchy management and latency hiding. Well, guess what? Databases are actually designed by people who really were worried about the memory hierarchy because they had to go to disk all the time, right? Out of core and all that. So I don't think it's a hard sell for me to convince you that set-at-a-time processing, et cetera, in a database context is good from a memory hierarchy management perspective. The second one is parallelization. Well, guess what? I would argue SQL is by far the most popular example of an automatically parallelized language. Okay, most other programming languages, programming paradigms, you have to do the parallelization by hand. And SQL sort of, in large part, and relational technologies in large part hide that. Okay, and then the last bit, which hasn't been very popular in relational database land until maybe the last 5 years, is specialization and JITting and getting rid of interpretation overhead. Right. IBM studied this idea of compiling SQL down to machine code in the 70s, and it was so damn hard, and you couldn't make it work from machine to machine, and da-da-da-da. And so they wrote papers that poo-pooed it, and basically no one did it until a few years ago when new compilers and compiler infrastructure had been invented, like LLVM and so on, and it made it possible to do that. So systems like Redshift do a very crude version of this by taking SQL, emitting C code, writing it to disk, calling GCC, having that compile into machine code, and then dynamically linking that back into Redshift and then giving you the answer. That's one way of doing it, but the overheads are high and the debugging is a nightmare and so on. Okay, so we were looking at, let's look at the last one, right? I don't think I have to sell you on being able to do the first two. The last one is really important to us. It's just an innovation in this company that we didn't do at LogicBlocks. But we didn't want to spend 5 years implementing JITting in a database. So we just didn't have the time or the money or the interest, frankly, having spent 3 to 5 years building LogicBlocks in C++. So we're doing something that will get you to chuckle, at least initially, which is instead of implementing in a language for systems, we're implementing in a language that normally people don't think of as system implementation language, okay? So, so Julia, for those of you who don't know Julia, is sort of aspires to be a dynamic language that can be compiled down to very, very efficient code if you write type-stable, what they call type-stable Julia code, okay? And I'm going to show you 2 examples of how we apply that. First example is in query evaluation. So now normally when you're building a database, you have to, when you compile the database down, you have to make sure that database works for any schema, any data set, any query. But at some point, you get a schema, you get a data set, and you get a query. So in principle, if the problem is just that data, that schema, that data, that query, you don't need all that flexibility. The specialization is compile that flexibility away. Okay, I don't want to pay the price for the generality at the point that I know the data, I know the schema, I know the query. Okay, so I want to have something that's written this way, emit at something looks like this. And as I mentioned, there are many ways to achieve this. From a software engineering perspective, they can be quite daunting. I mentioned the Redshift way. There are other ways that you might have seen, people publish about, like LegoDB and LMS and Squid. There's work that's being done at Stanford and EPFL and a variety of places that use languages with a very rich type system like Scala to do multi-stage programming and the Futomura projection, which means that, hey, you write me an interpreter, and the compiler will specialize that and make that interpreter into your language will make that interpreter into a compiler that for the language, right? So the idea is I want to do software engineering work that's proportional to writing an interpreter, and I want my language to give me a compiler as a result. Okay? So anyways, for reasons I can't explain super convincingly, Julia is something like a fragment of the TPCH query 1, like this here, and we shrunk it down just to make it fit on one slide. Obviously, this works for all the queries. What we do, what our compiler does, and what our query optimizer does and all that, is it takes that and emits this Julia code. Okay, so we compile down to Julia, and then we let Julia compile down to LLVM IR, and we let LLVM compile down to machine code. And this is not a made-up example. This is all of the machine code that implements this SQL query. Okay, and hopefully you get a sense from the fact that it's not a lot of machine code, that it's tight, and it's not machine code that's just interpreting the query. It's machine code that is evaluating overhead that you have to have, like, for accommodating variable length relations and variable hierarchy relations and so on and so forth. Okay? And in fact, there are variants of this that get vectorized or SIMDified on our behalf by LLVM. We don't have to write all those low-level optimizations. Okay, so what does that mean in practice? So for TPCH, for scale factor 100, so 100 gigabytes of data, not a lot of data, but also not an inconsequential amount of data, we're running on Spark using their implementation of TPCH on their hardware tuned by them. Okay, so this is their showcase implementation of a TPCH benchmark. This is how much time it takes Spark on 8 cores, 16 cores, 32 cores, 64 cores. This is how much time it takes to run Hyper, which is the engine embedded in Tableau and obviously developed by Thomas Neumann. And very, very high performance, considered one of the best BI engines. And then Spark on 128 cores, and then RelationalAI on 1 core for this benchmark. Now, caveats. Caveats are the query evaluation mechanism that we use here is completely general, but what we did is we manually came up with the execution graph, right? So we manually optimized variable order and things like that. Our friend here, Dan, and others in our faculty network and our team are working on the optimizer that will generate the same query plans that were used here, okay? So it's not fair to Hyper, and in the sense that Hyper had to kind of optimize the query directly, okay? But it is also not, the point should still be valid here, is that in our general purpose query evaluation mechanism, if you give it a good query plan, it will do really well, okay? And then the thing that worst case optimal join algorithms are known for, optimizing graph queries in particular. This is an example of the triangle query, running it on various flavors of Spark, various implementations of graph analytics on Spark, which I'm sure some of you know are not that great. Okay, so in the interest of time, I'll skip through this other example. This is more like a software engineering example, like Peter Bonch is one of our advisors in our faculty network, and he's used to building, he knows how to build high performance database systems. And so, for example, if you wanted to add rational numbers to a database system, or fixed precision numbers to a database system, it's not just like you have a type and you add that type and everything works. It's often the case that you have to expose the details or the internals of that type to the query evaluation mechanism to make sure that it's optimal, right? Because there are overheads associated with the abstraction that you want to eliminate if you want a high-performance database engine. And so the nice thing about using something like Julia is we just took the Julia fixed precision decimal type, okay, and then embedded it into our system without having to make our query evaluation system at all aware that this type exists. Anyways, to make a long story short, the jitting and this time specialization and so on gets rid of the abstractions. So our system is a lot less code. So Logic Blocks was about 330,000 lines of code in C++, not counting the compiler. At RelationalAI, we're basically at 78,000 lines of Julia code right now. We're not done, so maybe that will double. But we expect the new system to be substantially smaller than the old system. Okay? And the last thing I would say about Julia is there's a lot of work being done by other people to map Julia to GPUs and TPUs and things like that. At some point, we're going to play around with that, and hopefully it will work out for us that we'd be able to leverage that investment. Okay? So that was the third point. Okay? The third point is that you can build relational systems in a way where your constant factors are really good. And so it's not a trade-off between asymptotics and constant factors, right? You can get all the TensorFlow type optimizations done in a relational context, I believe, I maintain. Hopefully I've shown you some evidence of that. And you get the asymptotics that exploit problem structure that you only see if you have the schema, you have the relational knowledge. Okay, and what do you use this stuff for? How are we going to make this work in the marketplace? There is a trend in the database world to try to bring the machine learning system and the data management system together, but it tends to be very superficial. Like BigQuery has machine learning built in. I don't know exactly how BigQuery is built, but I'm willing to wager that it's a relational engine and TensorFlow, and there's a surface language that ties them together, but that design matrix is still being built underneath the covers, and that the machine learning actually doesn't have visibility into the relational structure that's there. Okay? But it is a step in the right direction to bring data management and machine learning together, I think, and that's better than nothing. Now, what we're doing, as I'm hopefully giving you, clarity on, is that we're rethinking storage, the data structure, the query evaluator, the query optimizer, the front end, all of it for the machine learning use case. So our systems will handle the machine learning stuff natively. It will handle the business intelligence use cases, the graph use cases, the planning use cases. It just worked out that in order to build a database that is AI aware, you get the components that like aggregation that make you really good at BI, and you get the components like graph queries, et cetera, that the join algorithms that make you good at graph queries and so on. I'll close by saying that what we ultimately want to evolve this to, because we don't think you just put this out there and people will start to use it, because people still are going to be comfortable with their Spark and with their TensorFlow and all of that, is that sort of there's an emerging class of applications that the venture community is calling operational analytics or AI-infused operational analytics that go from beyond sort of the basic bookkeeping and the basic BI that was used to support rote work. So this idea of digital transformation and things like robotic process automation and so on is all about taking a big companies like Boeing or like Amazon or like Nordstrom's and companies here in the Seattle area and automating away the rote work. But when you do that, what you're left is more decision-making work. So instead of spending 4 hours a day doing rote work and 1 hour or 2 hours a day doing decision-making, now your typical worker is going to be spending more of his or her time doing decision-making. And this is where machine learning can help in an enterprise context, okay, which is any decision can be made better or improved if you can predict the outcome of that decision. Like what happens when I promote the organic blueberries? Well, if I can predict that sales of my normal blueberries are going to go to hell and I'm going to end up throwing away a lot of them, then maybe I wouldn't do that, okay? So applications for operational decision-making and operational analytics need to be built differently than applications for business intelligence and applications that support rote work. And our thesis is that this new category of technology, relational artificial intelligence, at the intersection of relational data management and artificial intelligence, is going to be really important for the development of those kinds of applications. So you don't have to stitch together 20 different tech stacks to kind of put one of these together. All right? And with that, I will just show you very quickly. There's a lot of really deep work that's happened here on join algorithms, on query optimization, query plans, on in-database machine learning, and also work done by people outside of our company on Julia and modern compilers and so on. Thank you.
So we do have time for questions.
Magda.
So one question. So you really showed us kind of two types of optimizations, if I will call them, right, in this talk, and they really seem orthogonal. So it seems like if someone else is building an engine, they could take the first part of your talk and apply these techniques, or the second part of your talk and apply your techniques.
That's right. No, they're orthogonal. The constant factors are orthogonal from the algorithms. And that's a good thing. And but we think that you need both to compete effectively with sort of the traditional way of doing machine learning. And so, if we had really good algorithms, but we didn't take care of the constant factors, I think that will always be a knock, GPUs in memory, kind of testosterone-filled optimizations still matter to people, right? And you need that, I think, to complement the elegant, smart brain approach. Sometimes you just need muscle.
Yes, please, Eugene.
There is increasing amount of data that is stored denormalized or semi-denormalized. Like people insert JSON and then it gets shredded into columnar representation. And relational databases, we don't know how to use the query processors on that data efficiently. You think that these same approaches can be applied to this kind of data?
I have high confidence that in JSON in particular, the way that, I didn't have time to get into this, but the way that we translate semi-structured JSON documents into 6 normal form relational schema. So again, when I'm talking relational here, I mean like mathematical relational. I don't mean SQL relational, okay? I mean, SQL is long in the tooth, and we fully intend to support it in order to go to where SQL and BI analysts are, to meet them where they are. But you've seen systems like Snowflake and many other database systems sort of try to bring JSON documents into the relational database in a way where they can be queried relationally. And I think what we've done makes a small but nice contribution to that, so that your JSON document is 6 normal form relational database.
Yes, please.
You mentioned sufficient statistics to compute, let's say, this transfer of gradient from the row matrix form to the relational form. And then you mentioned certain algorithms covered in this scheme. I'm curious how extensive is it to other which are not yet supported by Relational?
Yeah, it's a research grade question. Dan and Max will be better at answering.
Can you repeat the question?
Oh, sorry. The question is, we talked about sufficient statistics and computing them so that we can push the gradient descent through the view that defines the design matrix. How general, how broadly applicable is that, right? And so I put up this list of methods. So you read Max's papers, linear regression, polynomial regression, factorization machines, both theoretically and in practice have been implemented, and we know that we can do that relatively well. Now, your ability to capitalize on this optimization depends on the feature engineering work that you do. And if the features that you're building require a lot of aggregation, et cetera, there's going to be less of a difference between the size of your design matrix and the size of your relational structure. Decision trees, I think the theory is established, but we haven't, at least at RelationalAI, we haven't cracked the code on how to implement them efficiently. I think Max might have in his system. And in particular, boosted decision trees, we don't know, at least I'm not aware that we know exactly how to deal with the boosting. And some of the math on these other methods have been worked out. I think we submitted a Europe's paper on k-means and median, k-median clustering. So really, it's so for the optimizations we've implemented, my understanding is we're exploiting a semi-ring property of the problem. And so if your problem breaks down to addition and multiplication or min and max or things that fit into a semi-ring, then that loss function has that structure and your method is implemented in terms of a loss function that has the semi-ring properties, then we can optimize. That's my understanding. But really, ask Max.
So actually, I have a question. So in the same spirit, so you talked about applications that of machine learning that can be, that should be converted into relational processing. But can you talk a little bit about applications that are beyond the reach of relational models? I'm thinking about vision and NLP. What are your thoughts about the border between what can be relational and what cannot be?
So certainly we have a lot of respect for all the machine learning work and AI work that's being done on perception problems, which is images, not a lot of structure there, at least initially. Obviously, as you start to recognize the ball and the boy in the car and a boy running after the ball about to get hit by a car, that becomes more of a relational problem at that level, right? And things like speech and text and so on. Those are not an area of emphasis for us. But Dan, as you know, I think relational systems can be evolved into handling dense data well. And I don't mean like by adding a blob type as a type into the database. I mean by having a row, column, pixel kind of mapping. And so as a research problem for many years down the road, it would be nice to see to what extent you can support dense data sets, okay, natively in the relational model from an implementation perspective. Obviously, mathematically, it's already supported, but the implementations are what matter here, or where the obstacle is here. So, but for now, we're not doing anything with that stuff. Perception is for TensorFlow and deep learning.
Okay, so I think this is all the time we have. So let's stop here and thank Molham.
Thank you.